Bismillahirrahmanirrahim and welcome everyone. Today we are going to start the next topic of the chapter states of matter, and that is the Charles law. This law was first presented by the J.Charles in 1780s. But this law remained unpublished till 1802 when Gay-Lussac again studied the effect of the temperature on the volume of the gases, and he published this law. But he gave full credit to the J. Charles, and this law was named after the J. Charles as the Charles law. Now, this law studies the relationship between volume of the gases with temperature, or more precisely, you can say absolute temperature. What is meant by the absolute temperature we are going to discuss in this lecture. But when we study the relationship of the volume with the temperature, at that time the quantity of gas or number of moles and applied pressure, they will remain constant. So number of moles and applied pressure, they are the constants of the Charles law, while the volume of the gas and the absolute temperature, these are the variables of the Charles law. Charles law states that volume of given mass of a dry gas varies directly with absolute temperature at constant pressure. So this one is the statement of the Charles law. Mathematically, it can be written as the volume is directly proportional to absolute temperature or Kelvin temperature if N and P they remain constant. You can also write it down as V is equal to K into T when N and P are constant. K is the proportionality constant, or we can say it as the ratio between the volume of the given mass of a gas and absolute temperature remains constant if the quantity and pressure is constant, or the ratio between initial volume and initial absolute temperature, that is equal to the ratio between final volume and final absolute temperature of the gas. The conditions are same. This one is a very important form, and it can also be rearranged as V1 into T2 is equal to V2 multiplied by T1. So these are the different mathematical forms of the Charles law. Means if the temperature of the gas decreases, then the volume also decreases, and if the temperature increases, then volume of the gas also increases provided that the number of moles and pressure are constant. And this form of the Charles law is obeyed only if the temperature is taken on Kelvin scale, or you may say absolute scale of temperature. If the temperature of a gas increases 2 times, then the volume also increases 2 times. And if the temperature becomes half, then the volume also becomes half. So it is the direct relation between the volume and temperature of the gas. Now, there is another form of the Charles law. Another form of Charles law. According to this another form of Charles law, at constant pressure, volume of given mass of gas increases or decreases by 1/273 times of its volume at 0 degree C for every 1 degree C increase or decrease of temperature respectively. This is another form of the, or rather another statement of the Charles law, that if the pressure is kept constant and you increase the temperature of the gas by 1 degree centigrade, then the volume will be increased by 1/273 times of what the volume of the gas was at 0 degree C, means the original volume of the gas. The original volume is actually the volume of the gas at 0 degree C. Mathematically, this form can also be written as Vt is equal to V naught 1 plus T by 273. V naught is the volume of gas at 0 degrees C, and it is also called as the original volume of gas, while this T is the temperature at 0 degrees C. This is the temperature at degree Celsius scale. So this form is valid when you will take the temperature at degree Celsius, and this form or these forms will be valid when you will be taking temperature at the absolute scale or the Kelvin scale. So this form is very important in a sense that we can find the volume of gas at any temperature T. This is the volume of gas at any temperature T, provided that we know the original volume or volume of the gas at 0 degrees C. Suppose that we are taking temperature is 273 degrees C. Original volume is V naught. Then what will be the volume at 273 degrees C? Applying this formula, volume at 273 degrees C is equal to V naught 1 plus 273 over 273, and you will solve it. V1 V naught into 1 plus 1, that is equal to 2 into V naught. This simply means that the original volume of the gas doubles at 273 degrees C, or if you are taking it on the Kelvin scale, that will be the 546 Kelvin. Now let us find the volume of a hypothetical gas at minus 273 degrees C using this formula. So let us apply this formula, and you will get that V minus 273 degrees C is equal to V naught 1 plus minus 273 divided by 273. This will be 1 minus 1, and that will become 0. So it simply means that the volume of the hypothetical gas becomes theoretically equal to the 0 at minus 273 degrees C. Practically, it is not possible to achieve minus 273 degrees C, which is equal to the 0 Kelvin. Now this temperature, minus 273 degrees C, that is equal to 0 Kelvin, and that is equal to minus 459 degree Fahrenheit. And this temperature at which the volume of the hypothetical gas becomes equal to 0, this is called as absolute 0. 0 Kelvin is the absolute 0, and its value on the degree Celsius is minus 273 degrees C, and on degree Fahrenheit is minus 459. What is meant by the absolute here? Actually, the word absolute means infinite cold. Absolute 0 actually means infinite cold temperature. And this is called as absolute temperature or absolute 0 because technically kinetic energy of molecules becomes 0 at this temperature. Absolute 0 means it is an infinite cold temperature for the gases. And at this temperature, the molecular motion ceases. The kinetic energy becomes 0. All forms of the kinetic energy, whether they are translational, rotational, vibrational, they become 0. Now, does it happen practically or experimentally? Is it true that the volume of a gas becomes 0 at minus 273 degrees C? So practically, till now, it has not been achieved. Means, first of all, the hindrance is that minus 273 degrees C, that is a very, very, very low temperature. And up till now, scientists have not found any way to achieve this kind of the low temperature. No doubt that they have reached very close to this absolute 0, and the lowest temperature achieved so far is 10 raised to power minus 5 Kelvin. That is very close to the 0 Kelvin. Fractionally it is more than the 0 Kelvin, but still it is not 0 Kelvin. It is greater than the 0 Kelvin. Fractionally greater, but it is greater. So 0 Kelvin, that has not been achieved so far. There is a second hindrance. Suppose that in future, according to by using some techniques, if the absolute zero is achieved and the temperature of minus 273 degrees is achieved, then would it be possible for the gases that their volume will become zero? No. Now what is the second hindrance? The second hindrance is that the critical temperature of all the gases, that is greater than minus 273 degrees C. So before reaching to the minus 273 degrees C, the gases will liquefy, or even some gases will solidify. So now you will have to keep the gas in the gaseous form, that is the first target, and you will not let the gas to be liquefied or solidified. And secondly, you will have to achieve this low temperature. If these two things they can be done, then the volume of gas can practically become zero. But it seems to be impossible because it is against the law of conservation of mass or matter. Because according to law of conservation of matter, the matter cannot be destroyed or created. So when the volume of the gas will become zero, it simply means that the gas will be destroyed, which is against the law of conservation of mass. So it is not going to happen practically in the near future and in the future. It doesn't seem to be possible. Now, why Kelvin scale is called as absolute scale? Because the reference point of the Kelvin scale is absolute zero. That's why it is called as the absolute scale of temperature. While the reference point of the degree Celsius and degree Fahrenheit are, the melting and boiling points of the water. Or you can say the freezing point and boiling point of the water. So the reference in degree Celsius and degree Fahrenheit is water. And whenever you are taking some temperature at degree Celsius or degree Fahrenheit, so it actually means you are comparing the kinetic energy of that substance at that particular temperature with water, because the reference is water. But when you are taking value on the Kelvin scale, it is with the reference to the absolute zero. And because absolute zero is the reference, so that's why it is called as the absolute scale of temperature. It is also the System International basic unit of the temperature, because it fulfills all the requirements of the standard temperature. So that's why it is the System International unit of temperature as well. Now you can see that we put the sign degree on Celsius, we put the sign degree on Fahrenheit, but no degree sign is used for the Kelvin scale. The reason is that this scale is the only scale that has no negative value. Its lowest value is 0. And degree means that you are going to decrease some value and you are going to decrease it below the 0, which is not possible in the Kelvin because the lowest value is the 0 Kelvin. While degree Celsius and degree Fahrenheit, they use degree sign because they have negative values and their negative values are achievable. So that's why the degree sign is used for the Celsius and the Fahrenheit scale. Now at the last, let us discuss the Charles law graphically, that if a graph is plotted between volume and temperature, then what kind of picture we are going to have. So the graph can be drawn in two ways. This one is x-axis, y-axis, On x-axis we are taking temperature on Kelvin scale, and on y-axis we are going to take volume in decimeter cube or centimeter cube, whatever value or whatever unit you can use here. Any unit can be used. When the graph was plotted, we obtained a straight line which simply shows that volume of the gas and temperature or absolute temperature, they are directly related. This graph that is drawn at the constant pressure, so that's why it is called as isobar. The graph of the Boyle's law is called isotherm because it is drawn at the constant temperature, and here the graph is drawn at the constant pressure, so that's why it is called as the isobar. But this straight line that does not touch the origin of the graph. Why? Because 0 Kelvin is not achievable, and even the volume of the gas is not going to be 0 at any cost. But if we extrapolate it, extrapolation means we are going beyond our scale or beyond our practical values, then it does touch the origin, which means that theoretically it is a correct discussion that at 0 Kelvin the volume of the gas will be 0, but practically due to some limitations it is not possible. Now this straight line is obtained at pressure P1. Suppose that we increase the pressure in the second experiment, then the straight line like this is achieved. The line is still straight, its shape is not changed, but the position of the line changes. It moves away from the y-axis towards the x-axis. This one is the straight line obtained at pressure P2, and P2 is greater than P1. Why it moves away from the y-axis towards the x-axis? Because when we increase the pressure, it results in compression of a gas. So due to compression of a gas, the position of the line, it changes. Suppose that at a particular value of the temperature T, what will be the value of volume at pressure P2? That is V2. And what is the value of at P1? That is V1. You can clearly see that the V2 is less than V1 even at the same temperature. So it simply shows that when you have increased the pressure, the compression of the gas takes place or the volume of the gas decreases. Now this graph can also be drawn in the way something like this. Here again, there is temperature on the x-axis in degrees Celsius and volume on y-axis. Suppose here is 0, 200 and so on. Here is minus 200, minus 300 and something like a scale like this is developed. Then you will again get a straight line. And now this straight line will also be an isobar. And when you will extrapolate it, it will touch the graph. It will touch the x-axis on a value minus 273 degrees almost. It is also an isobar, and similarly if you will change the pressure, it is at P1. When you will change the pressure, again you will get a straight line that will be away from x-axis, away from y-axis towards the x-axis, means P2 is greater than P1. But when you will extrapolate it, it will again touch at the minus 273, which simply shows that it is correct that the volume of the hypothetical gas will become 0 at minus 273 or 0 Kelvin, but practically it is impossible. So that is the graphical explanation of the Charles law. Now, there are some daily life applications of the Charles law, like you can see that in a very cold weather, the balloons, the helium balloons or other balloons, they shrink. Why? Because the temperature of the surroundings decreases, due to which the volume of the gas also decreases. Similarly, in the winter, the lung capacity of the human beings that also decreases due to very cold weather, and it becomes very difficult for the athletes or the sportsmen, or for those people that are performing jogging, uh, they are jogging in the cold weather. It becomes very difficult jogging in the cold weather or performing some activity related to the sports, because the lung capacity decreases and the oxygen intake in the cold weather that also decreases. So this was all about the Charles law. I hope so that it will be quite informative for you people, and inshallah next time we will come up with the Avogadro's law, that is the third law after the Boyle's and the Charles law. Till then, take care. Allah Hafiz.